You pick seat G7. It turns green. You hit pay. The spinner turns. Confirmation lands seat G6, not G7. Cinema Seat Allocation. Picture a movie theater with n rows, each holding 10 seats numbered 1 through 10. You're told which seats are already taken, and your job is to figure out the maximum number of 4-person groups you can seat together, since each group needs 4 seats side by side in the same row, chosen from a few specific blocks of seats. Hey, I'm Kai. Welcome back to Fun with Learning Technology. Today we are breaking down the logic sitting underneath that whole mess, cinema seat allocation. You get a cinema with some rows of 10 seats each and a list of seats already reserved. We need the maximum number of groups of 4 we can seat together. 2 people load the same seat map. Both see G7 as open. Both click it at nearly the same instant. Only one booking can win, but the app didn't check in time. Let's shrink this way down. Say we've got one row of 10 seats and seats 2 and 3 are already reserved. Everything else is open. How many groups of 4 can we seat together in that one row? Hang on to that number. We'll come back to it. Strip away the graphics. A cinema hall is just a grid. Each seat is a cell, free, held or booked. Locking G7 stops 2 people from booking the same seat. It doesn't find 4 seats together in the first place. And this hall only allows 3 exact blocks, not any 4 seats side by side. That search has to run fast, across rows that could number in the thousands. Say a group of 4 want seats together. Scan the row left to right. Track a running streak of free seats. Hit seat 4 in a row. That's the match. Here's the catch. This problem only counts 3 exact blocks per row. Seats 2 through 5, 4 through 7 or 6 through 9. And here's the mistake people actually make. They see one row, one group and stop as soon as they've placed a group. Because block B and block C overlap on seats 6 and 7, so it feels like a row is capped at 1. It isn't. Block A seats 2 through 5 and block C seats 2 through 5 and block C seats through 9 share nothing. So a totally empty row seats 2 groups at once, not 1. Back to our tiny room, seats 2 and 3 reserved. Block A needs seat 2, so it's out immediately. Block B, seats 4 through 7 is completely open. Block C, seats through 9 is also open. Block A, seats 2 through 9 is also open. Block C, seats through 9 and seat 2 nothing so too. Seats 1 and seat 10 never. 2 small tools make this fast. Since only rows that actually have a reservation matter, a dictionary that only stores those rows means empty rows never even show up. And inside each row, we pack which of seats 2 through 9 are reserved into one number. So checking a whole block becomes a single bitwise, and before we optimize anything, this is what that check looks like in code. We only try 3 starting points, 2, 4 and 6. And for each one, check whether all 4 seats in that block are free. First one that works, we grab it. Checking a list seat by seat works, but it's needless work when we can check a mask directly. For every reservation between seat 2 and seat 9, we flip 1 bit in a number for that row. Seat 1 and seat 10 never get recorded since they can't block any block. A, B and C are just those 3 blocks written as bits. Any row that never shows up in the dictionary is fully empty, and an empty row always splits 2 groups, since block A and block C never overlap. For a row that does have a reservation, we combine its mask with each block using bitwise AND. If the result is 0, that block is completely free. Put together, that's the whole solution. We build one small dictionary of masks only for rows that actually have reservations, then walk through it checking those 3 blocks. Every other row, the ones with nothing reserved, gets counted up front as 2 groups each. Let's run it on the real example. 3 rows, seats 2, 3 and 8 reserved in row 1, seat 6 in row 2 and seats 1 and 10 in row 3. Row 1 has block B free, so that's one group. Row 2 has block A free, another group. Row 3 never even makes it into our dictionary, so it's counted as fully empty up front. 2 groups. 1 plus 1 plus 2 is 4, which matches the expected answer. We only ever loop over the reservations themselves, once to build the masks and once to check them. So this runs in big O of the number of reserved seats. Space is the same. We only store rows that actually got a reservation. When you click a seat, it's not booked yet. It's held, locked to you for a few minutes. Anyone else sees it as unavailable during that window. If you don't pay in time, the hold expires and it's free again. Placing the lock has to be one atomic step. Check if free and mark as held happen together. No gap where 2 locks can both succeed. The grid tracks what's free. The window narrows the search down to the few blocks worth checking, instead of every seat. The atomic lock, separate from what we coded today, is what a real booking system adds on top to stop two people grabbing the same seat. That cinema seat allocation, count fast, then let the system layer safety on top. Quick quiz. Two guests grab seat 5 in the same row at the exact same millisecond. What actually stops the double booking? Pause and take a guess. Think back to that timing gap we opened with. It's the per row lock. Only one thread can update a given row at a time. So the check and the set happen as one atomic step, no race. Round 2. A row has 10 seats. Which seats can actually start a group of 4? Not every seat works here. Think about why. Then guess. Remember the rule about fixed blocks. Only seats 2, 6 and 10. Those anchor the 3 fixed 4-seat blocks, so we are never scanning the whole row. Just checking 3 fixed spots. Talk is cheap. Let's actually run this. I fed it all 3 of the problems, real examples. No cherry picking plus 3 extra edge cases. I pick myself.